Water is the lifeblood of industry. From semiconductor fabrication to food processing, from power generation to automotive manufacturing, water enables production, cools equipment, transports materials, and ensures product quality. Yet as global populations grow, climate patterns shift, and freshwater resources become increasingly stressed, industries face a fundamental question. How can we continue to produce the goods society needs while reducing our impact on finite water supplies? The answer emerging from leading facilities around the world is industrial water reuse, the practice of capturing, treating, and returning water to industrial processes rather than discharging it after a single use. The promise is compelling: reduced freshwater withdrawals, lower wastewater discharge volumes, compliance with tightening environmental regulations, and enhanced operational resilience. With over 500 facilities already recycling water across the United States, the business case for reuse is becoming increasingly clear. But closing the industrial water loop is not simply a matter of installing treatment equipment and declaring victory. Every reuse decision involves trade-offs between water recovery and energy consumption, between treatment intensity and operational complexity, between capital investment and long-term savings. As the U.S. Department of Energy emphasizes, treating water for and from industrial processes is an energy-intensive process. The challenge is not just to reuse water, but to do so while managing concentration, energy, treatment, and compliance risks effectively. This documentary presents a comprehensive framework for understanding and implementing industrial water reuse. We will explore the context that makes reuse increasingly essential, the treatment trains that make it possible, the critical trade-offs between concentration and energy, the applications in cooling and process water, the monitoring and compliance requirements, the limits and risks that must be managed, and a practical checklist for implementation. Throughout this investigation, we will maintain clear distinctions between observed facts, well-supported assumptions, illustrative examples, and actionable recommendations. The goal is to equip decision-makers with the understanding they need to close the loop, without hiding the trade-offs. To understand why industrial water reuse has become a strategic imperative, we must first understand how water is used in industry. Water serves multiple functions in manufacturing: as a raw material incorporated into products, as a cleaning agent, as a cooling medium, as a solvent, and as a transport mechanism. The scale of industrial water consumption is substantial. The production of a single vehicle, for instance, can require more than 1,000 gallons of water. Semiconductor fabrication facilities, or fabs, consume millions of gallons each day, with nearly 76% of water withdrawn used directly in manufacturing processes. Data centers, which power the digital economy, consume enormous volumes of water for cooling systems. This dependence on water creates both operational and strategic vulnerabilities. Observed fact: water stress is expanding across the United States, with intensifying interdependencies between energy, water, and greenhouse gas emissions. This is not merely a Western U.S. phenomenon. Water scarcity is becoming a national concern that affects industrial operations in regions previously considered water secure. Observed fact: the U.S. Environmental Protection Agency's Water Reuse Action Plan 2.0, launched in April 2026, explicitly frames water reuse as a strategic resource for economic competitiveness, rather than solely as a water scarcity response. The plan targets 3 high-impact sectors: domestic manufacturing, including automotive, food and beverage, and battery production; technology, including semiconductors and data centers; and energy infrastructure. Observed fact: the U.S. Department of Energy is funding research, development, and demonstration into water reuse and desalination technologies through the National Alliance for Water Innovation Hub, which unites academia, industry, and national laboratories to research ways to open non-traditional water sources for human use. Stated assumption: the drivers for industrial water reuse will continue to intensify. As the Department of Energy notes, obtaining cost-effective water sources for manufacturing while reducing industrial energy use is critical to ensuring the sector's global competitiveness. This implies that facilities that do not adopt reuse strategies may face increasing competitive disadvantages. Stated assumption: the technologies for water reuse are maturing rapidly, making implementation increasingly feasible. The Water Reuse Action Plan operates on the premise that advances in treatment technologies are opening new applications for reclaimed water. Illustrative example:
In Arizona, the Palo Verde Generating Station, the only nuclear plant in the world not located on a body of water, already uses more than 20 billion gallons of recycled wastewater annually. This demonstrates that large-scale industrial reuse is technically achievable, even in water-scarce regions. Illustrative example. In Loudoun County, Virginia, more than 745 million gallons of recycled water were supplied to data centers in 2025 alone. Micron Technology, the only U.S. computer memory manufacturer, has committed to 75% water conservation in its operations by 2030, with reuse playing a central role. Recommendation. Industrial facilities should conduct a comprehensive water balance assessment to quantify current water use, identify the largest consumption points, and evaluate the potential for reuse.
Conduct a comprehensive water balance assessment to quantify current water use, identify the largest consumption points, and evaluate the potential for reuse. This assessment should include both direct water costs and the hidden charges of water and discharge fees, compliance risks, and potential supply disruptions. As UNIDO's experience demonstrates, resource efficiency assessments that map the full flow of water, energy, and materials through production processes can identify significant opportunities with modest investment. Once the decision to pursue water reuse has been made, the next critical step is designing the appropriate treatment train. This is where technical rigor meets practical reality. Not all wastewater streams are created equal, and not all require the same level of treatment. Observed fact: industrial wastewater streams vary dramatically in their quality and treatability. Cooling tower blowdown, which is characterized by high total dissolved solids and scaling potential, presents different treatment challenges than process rinse water, which may contain low concentrations of specific contaminants but requires high purity for reuse. Sanitary wastewater differs from both. Observed fact: water reuse systems that treat all facility wastewater to a single high-quality standard are generally more expensive and energy-intensive than systems that match treatment to the intended reuse application. As one industry observer notes, long-term success depends less on how much water is recycled and more on how well reused streams remain compatible with production realities. Observed fact: the U.S. EPA's Water Reuse Action Plan includes an action to establish a decision-making framework for water reuse in food and beverage production, recognizing that different industrial sectors have unique requirements and challenges. Stated assumption: source segregation, keeping different wastewater streams separate, is generally more efficient than treating mixed streams. A stream that contains only heat, such as cooling water, may require minimal treatment before reuse in non-critical applications. A stream containing specific process chemicals may require targeted removal of those chemicals. Diluting contaminated streams with clean streams rarely makes treatment more efficient. Stated assumption: the concept of fit-for-purpose treatment, treating water only to the quality required for its intended reuse, offers the most cost-effective approach. This avoids the energy and cost penalties of overtreatment. Illustrative example: in a textile dyeing facility studied by UNIDO, treated wastewater was no longer discharged fully into the environment. After meeting regulatory standards, the water was further purified through ultrafiltration and reverse osmosis before returning to the production line. In 2024, the facility reused nearly 60,000 cubic meters of water, equivalent to 26.7% of its total water consumption. Illustrative example: the standard ISO NP 20468-13, currently under development, addresses the performance evaluation of mechanical vapor recompression, or MVR technology, for treating high salinity wastewater from streams that present the greatest treatment challenges, including reverse osmosis concentrate, ion exchange resin regeneration wastewater, flue gas desulfurization wastewater from thermal power plants, and wastewater generated by semiconductor manufacturing, battery production, and coal chemical processing. Recommendation: implement a source segregation strategy that separates wastewater streams based on their composition and potential for reuse. This allows treatment to be tailored to each stream's specific needs. Recommendation: define reuse quality requirements by application, not just by regulation. Cooling tower makeup water requires different quality than boiler feed water, which differs from process rinse water. Matching treatment to the application avoids unnecessary costs. Recommendation: evaluate where nature-based and low-energy options can substitute for high-energy treatment units. For example, constructed wetlands can provide biological treatment for some industrial wastewaters with lower energy consumption than mechanical systems. As water is reused and recycled, the concentration of dissolved solids and contaminants increases.
This concentration effect is the fundamental physical challenge of industrial water reuse. Addressing it involves a series of technological and energy trade-offs. Observed fact: treating water for and from industrial processes is an energy-intensive process. The Department of Energy explicitly states that tapping into non-traditional water sources, such as treated wastewater, desalinated seawater, brackish groundwater, or water released as a byproduct during oil and gas extraction, requires more energy than accessing traditional fresh groundwater and surface water resources. Observed fact: conventional reverse osmosis systems typically recover only 50 to 80% of feed water, leaving 20 to 50% as concentrated brine. As recovery rates increase beyond this threshold, several technical challenges emerge: scaling and fouling, higher osmotic pressure requiring more energy and membrane stress, operational stability risks, and increased chemical demand. Observed fact: achieving zero liquid discharge is rarely a single-step process. Between conventional treatment and complete evaporation lies an intermediate phase, minimum liquid discharge, that minimizes the brine volume requiring final concentration.
Combining mechanical, membrane, and selective thermal processes, minimum liquid discharge can shrink the residual brine stream by 60 to 90%. Observed fact: mechanical vapor recompression, or MVR, is increasingly recognized as a key enabling technology for achieving zero liquid discharge objectives. MVR compresses and recycles the low-pressure vapor generated during evaporation as its own heating source. Through the recovery and reuse of latent heat by mechanical compression, MVR systems achieve high water recovery rates from high total dissolved solids wastewater at substantially lower specific energy consumption compared with conventional thermal systems. Stated assumption: higher water recovery almost always requires more energy. The relationship is not linear. As concentration increases, the energy required for separation increases significantly. This means there is an economic optimum for recovery that balances water savings against energy costs. Stated assumption: fully closed loops are theoretically attractive but practically fragile. As reuse cycles intensify, trace constituents that were previously negligible begin to concentrate. Without deliberate purge or dilution strategies, these accumulations gradually erode system stability. Stated assumption: the technologies available for high recovery systems are advancing. Research on pulsed flow reverse osmosis, fluidized bed reactors for controlled salt precipitation, and hybrid membrane thermal systems offers the potential for higher recoveries with lower energy consumption and extended membrane life. Illustrative example: in a power plant in Chile, a hybrid high recovery system achieved more than 93% water recovery from cooling tower blowdown, a challenging effluent known for high scaling potential. The system combined a fluidized bed reactor for controlled salt precipitation with a cyclic reverse osmosis operation that periodically flushed membranes at high shear velocity. This prevented scale buildup, stabilized flux, and reduced the thermal stage to a minimal polishing step. Illustrative example: for streams with total dissolved solids well above 50,000 milligrams per liter, membrane processes are generally limited. Evaporative concentration becomes necessary. MVR achieves high water recovery from such streams with lower energy consumption and carbon footprint compared with conventional thermal or multiple effect evaporation systems. Recommendation: model at least 3 scenarios when designing a reuse system: no regret water conservation, partial reuse for non-critical applications, and high recovery reuse or zero liquid discharge. This allows decision makers to understand the trade-offs between recovery, energy, and cost. Recommendation: accept that controlled discharge is often necessary to preserve loop integrity. Rather than pursuing absolute closure, define equilibrium points where reuse, purge, and makeup water remain balanced. This balance prevents progressive degradation while maintaining predictable operating conditions. Recommendation: structural reuse hierarchically based on sensitivity, exposure, and failure impact. Lower risk applications can absorb variability, while higher sensitivity processes receive more conservative inputs. This allows reuse to expand without uniformly increasing operational exposure. With the fundamentals of treatment and concentration understood, we can now examine specific applications of industrial water reuse. The 2 primary categories are cooling water and process water, each with distinct requirements and opportunities. Observed fact: cooling systems are among the largest water consumers in industry. Data center cooling systems alone can consume enormous volumes. Power plants are major water users for thermoelectric cooling. Reusing water for cooling applications often requires less rigorous treatment than reuse in production processes. Observed fact:
The EPA's Water Reuse Action Plan includes a specific action to support states in expanding the use of recycled water for industrial and data center cooling applications. The agency plans to compile and share best practices relevant for industrial cooling systems so states can readily permit the use of recycled water for data centers. Observed fact: process water reuse, returning treated water to manufacturing operations, is more challenging than cooling water reuse because of higher quality requirements. In semiconductor manufacturing, nearly 76% of water withdrawn is used directly in manufacturing, yet this is the stream least likely to benefit from recycling. Stated assumption: cooling water applications represent the lowest hanging fruit for industrial water reuse. The quality requirements are generally less stringent, the treatment technologies are well established, and the business case is often compelling. Stated assumption: process water reuse, particularly for high purity applications like semiconductor manufacturing, will require more advanced treatment and more careful management. However, facilities that already control the full life cycle of their water, from supply to discharge, have unique insight into water quality and the opportunity for safe reuse. Stated assumption: the trend is toward treating water reuse as an integrated part of facility design, rather than a standalone environmental project. As one expert noted, water projects should be treated as cross-functional environmental, health, and safety water projects, not only engineering initiatives. Illustrative example: in semiconductor fabs, many have adopted under-pipe zero liquid discharge systems to cool and reclaim water. However, most of the reclaimed water is diverted to cooling water.
Mechanical systems, such as scrubbers or cooling towers, do not return reclaimed water into the ultra-pure water systems that supply production. As one observer noted, this results in millions of gallons of ultra-clean reclaimed water being effectively wasted. Illustrative example: Singapore provides a model where all water used for ultra-pure water production is reclaimed from treated municipal wastewater. This approach reduces demand on freshwater supplies while also improving cost and energy efficiency within ultra-pure water systems. Recommendation: start with targeted, fit-for-purpose reuse applications before attempting 100% reuse. Cooling towers, irrigation, and non-critical washing are good starting points before tackling high-purity process water. Recommendation: for process water reuse, consider whether the stream must be treated to drinking water standards or can be treated to lower but still appropriate standards. As the EPA notes, reclaimed water for industrial applications can reduce pressure on drinking water supplies for communities across the country. Recommendation: if pursuing ultra-pure water recycling, investigate whether municipal wastewater is a viable source. As the semiconductor industry case illustrates, treating wastewater from outside the facility can sometimes be more cost-effective than treating internal streams. Water reuse systems require rigorous monitoring to ensure that water quality meets requirements, that treatment systems are performing as designed, and that compliance with regulations is maintained. This is where theory meets accountability. Observed fact: the EPA's Water Reuse Action Plan includes commitments to establish validation and monitoring protocols for treatment technologies and to explore digital solutions for real-time compliance tracking. This reflects a recognition that robust monitoring is essential for public confidence and regulatory acceptance. Observed fact: performance evaluation of treatment technologies is essential for technology selection, procurement, commissioning, and operation. The proposed ISO standard for mechanical vapor recompression systems aims to provide a common technical basis for evaluating these systems, supporting technology selection, procurement, commissioning, operation, and cross-project comparison. Observed fact: the U.S. Department of Energy conducts strategic analysis of water use in industry and a holistic assessment of energy use from wastewater treatment facilities. This includes technical assistance to help companies identify and implement energy and water-saving projects. Stated assumption: effective monitoring requires more than just measuring water quality at the point of discharge. It requires monitoring throughout the system: influent quality, treatment performance, reuse water quality, and system health indicators, such as membrane pressure and chemical consumption. Stated assumption: adaptive reuse architectures should incorporate monitoring and adjustment pathways that respond to gradual change rather than reacting to failure. This suggests that monitoring should be used proactively to detect trends and prevent problems, not just to document compliance after the fact. Stated assumption: digital monitoring and analytics are becoming increasingly valuable for optimizing reuse systems. Investing early in smart water systems and analytics rather than treating them as optional add-ons is a key success factor. Illustrative example:
Bird Energy, a program that fosters collaborative research between the United States and Israel, selected a project in January 2026 to develop the reuse of municipal wastewater via integrated PFAS separation and concentration. This illustrates the growing attention to monitoring and removing emerging contaminants in reuse applications. Illustrative example. UNIDO's test methodology, used for resource efficiency assessments, combines resource efficiency analysis with management practices to help companies track the use of materials, water, and energy, identify inefficiencies, and prioritize feasible improvement measures. Across 26 companies, this approach identified annual savings of approximately 9.7 million euros, alongside reductions of over 111 gigawatt hours of energy and nearly 449,000 cubic meters of water. Recommendation. Develop a comprehensive monitoring plan before implementing water reuse. This plan should specify what will be measured, including parameters and frequency, how it will be measured, using sensors and laboratory analysis, who will be responsible, including operators and management, what constitutes acceptable performance, including limits and triggers, and how data will be used for optimization, compliance, and reporting. Recommendation. Invest in real-time monitoring and digital analytics early in the project lifecycle. Digital monitoring and operator training are among the common success factors for reuse projects. Recommendation. Establish clear key performance indicators across water, energy, compliance, and uptime. Water reuse projects should be evaluated not just on water savings, but on their overall contribution to operational performance. Recommendation. Plan for training, succession, and documentation to avoid knowledge loss as personnel changes. Reuse systems are only as robust as the understanding of the operators who run them. No discussion of industrial water reuse would be complete without addressing the limits and risks. Closing the loop is not a panacea. It introduces new vulnerabilities that must be acknowledged and managed. Observed fact. High recovery reverse osmosis introduces technical hurdles, including scaling and stumbling.
Fouling, higher osmotic pressure, operational stability issues, and increased chemical demand are not theoretical concerns. They are observed phenomena that occur as recovery rates increase. Observed fact. Fully closed loops are attractive in theory, but fragile in practice. As reuse cycles intensify, trace constituents that were previously negligible begin to concentrate. Without deliberate purge logic or dilution strategies, these accumulations gradually erode system stability. Observed fact. The water sector's greenhouse gas emissions are projected to double by 2050, driven in part by the energy demands of water treatment. There is a risk that aggressive water reuse could increase emissions if not implemented with energy efficiency in mind. Stated assumption. The risks of water reuse are not limited to technical failures. They also include regulatory risks if systems are not aligned with compliance requirements, operational risks from insufficient training or complex control schemes, and financial risks from underestimating integration costs. Stated assumption. Different reuse pathways carry different operational risks. Reintroducing treated water into non-critical uses presents different challenges than reuse within core process steps. Failure in core processes can be catastrophic. Failure in cooling water may be manageable. Stated assumption. The risk profile of a reuse system changes over time. As production processes evolve, water quality characteristics may change. System performance may degrade gradually, which is why adaptive architectures are recommended. Illustrative example. The semiconductor industry's current practice of treating water to ultra-pure quality and then using it only for cooling and scrubbers is an example of a reuse pathway that does not maximize value. While it reuses water, it fails to address the main water demand, exposing the industry to continued reliance on fresh municipal supplies. Illustrative example. For facilities that cannot justify advanced reuse or zero liquid discharge immediately, incremental effluent upgrade technologies and basic water conservation often deliver better short-term value. This illustrates that the risk of overinvestment in ambitious reuse systems is real. Stated assumption. Very small or low-margin plants may not justify advanced reuse or zero liquid discharge immediately. Not every facility needs to close its loop completely. Partial reuse may be the most appropriate strategy. Recommendation. Start with a clear-eyed risk assessment before implementing water reuse. Identify the specific risks associated with your facility's wastewater streams, intended reuse applications, and available treatment technologies. Recommendation. Prioritize modularity to adapt to evolving regulations and production.
Modular systems can be expanded or modified more easily than monolithic systems, reducing the risk of obsolescence. Recommendation: design for operational stability. Consider what happens when treatment performance degrades, when membranes need cleaning, and when operators make mistakes. Redundancy and fail-safes may be justified for critical processes. Recommendation: model financial risks explicitly. Consider scenarios where water prices do not rise as expected, where energy costs increase, or where the facility's water demand changes. Water reuse should be robust to a range of plausible futures. Drawing together the insights from our investigation, we can assemble a practical checklist for implementing industrial water reuse while managing the trade-offs and risks. Part 1. Strategy and business case. Quantify current water and discharge spend, including hidden charges. Water costs often include not just purchase price, but also treatment, heating, pumping, disposal, and regulatory compliance. Map water-related risks in your enterprise risk register. Consider supply disruption risks, regulatory change risks, and reputational risks. Set explicit targets for industrial water savings and reuse percentage. These targets should be ambitious but achievable, and they should be tied to business objectives. Model at least 3 scenarios: no regret conservation, partial reuse, and high recovery reuse, or zero liquid discharge. This allows informed decision making. Part 2. Technical design. Define reuse quality requirements by application, not just by regulation. Cooling water, boiler feed water, process rinse water, and other uses have different needs. Evaluate where nature-based and low-energy options can substitute for high-energy units. Consider all treatment options, not just the most advanced. Start with targeted, fit-for-purpose reuse applications before attempting 100% reuse. Build experience and confidence with lower-risk applications. Prioritize modularity to adapt to evolving regulations and production. Design systems that can be expanded or modified more easily than knowledge change. Part 3. Organization and governance. Establish a cross-functional steering group, including engineering, operations, finance, and environmental, social, and governance teams. Water reuse is not just an engineering project. Define clear key performance indicators across water, energy, compliance, and uptime. This ensures that trade-offs are visible and managed. Plan for training, succession, and documentation to avoid knowledge loss. People are the key to long-term success. Invest early in smart water systems and analytics. Use data for optimization, not just compliance. Part 4. Implementation and optimization. Prioritize modular solutions for faster deployment and easier scaling. Start small, learn, and scale up.
Schedule periodic optimization reviews with your technology partner to adjust set points, cleaning intervals, and reuse allocations. The system should evolve with experience. Accept that controlled discharge is often necessary to preserve loop integrity. Balance reuse with purge to maintain stability. Structure reuse hierarchically based on sensitivity, exposure, and failure impact. Protect critical processes from quality variability. Industrial water reuse is not a simple technical fix. It is a strategic discipline that requires balancing competing objectives: water recovery and energy consumption, treatment intensity and operational complexity, capital investment and long-term savings. Observed facts: water stress is expanding, and regulatory and market pressures are intensifying. The United States government has made industrial water reuse a strategic priority, with the Water Reuse Action Plan targeting manufacturing, technology, and energy sectors. Treatment technologies are advancing, with high-recovery reverse osmosis, mechanical vapor recompression, and hybrid membrane thermal systems offering new capabilities. Stated assumptions: the business case for reuse will continue to strengthen, the technologies will continue to improve, and the costs of not acting will increase. These are reasonable assumptions based on current trends, but they are not certainties. Recommendations: the path forward requires source segregation and fit-for-purpose treatment to match water quality to application requirements. Careful management of the concentration-energy trade-off, accepting that higher recovery costs more energy. Adaptive monitoring and governance to maintain system stability as conditions change. Honest acknowledgement of limits and risks, with modular designs and controlled purge to preserve loop integrity. And strategic sequencing, starting with lower-risk applications and building capability over time. As the Department of Energy reminds us, wastewater streams can be a valuable resource that can be refined from the byproducts generated by water and wastewater treatment, providing revenue to wastewater and desalination facilities,
offsetting waste disposal costs, and promoting efficient solutions for energy, water, nutrients, and other chemicals. The water that flows through industrial facilities today carries both costs and opportunities. The choice to reuse is not just an environmental decision, it is a strategic decision about how to manage resources, mitigate risks, and build resilience for the future. The water that falls on our cities and flows through our factories can be treated as waste to be disposed of or as a resource to be managed wisely. The choice is ours, and it begins with understanding the trade-offs.